Hello everyone, welcome back to the channel. I'm Ricky. Today, I'm going to continue share this book. What topics we have? Well, it's not a big deal. You can see the whiteboard. 9 key factors affecting laser welding quality. This episode will focus on how to get the more perfectly welding quality. So if you follow on this 9 key factors, generally speaking, you can get more welding quality. So let's get started.
Power and power density. Laser welding is driven by heat input. Power is the source, but power density is the control. Power density equals power divided by spot area. If the spot is large, energy spreads. If the spot is small, energy concentrates. For keyhole welding, you need high power density. If density is too low, you get conduction mode, shallow penetration, unstable bonding. If density is too high, you get excessive vaporization, spatter, and instability. In production, do not chase higher power blindly. Control 3 things together: power, spot size, and focus position. Stable penetration comes from stable energy density. 2. Welding speed. Speed controls interaction time between laser and material. Increased speed, energy per unit length decreases. Decreased speed, energy per unit length increases. Too fast, penetration drops, keyhole becomes unstable, lack of fusion appears. Too slow, overheating, wider heat-affected zone, collapse of molten pool, even burn through. Speed also affects fluid flow in the molten pool. Unstable flow leads to undercut, irregular bead, and poor surface. Always match speed with power. The target is consistent penetration with controlled heat input. Defocus position. The focal position defines where energy is concentrated. At focus, energy density is maximum. Move away from focus, density drops. Positive defocus spreads energy before reaching the surface. Negative defocus drives energy into the material. For most metal welding, a slightly negative defocus improves penetration. Typically, focus is set just below the surface. If defocus is too large, energy becomes diffuse. The weld becomes shallow and unstable. Fine adjustment of focus is often the final step to optimize weld quality. 4. Welding angle. The ideal beam is perpendicular to the surface. At 90 degrees, reflection is minimized and energy absorption is maximized. When the angle increases, the spot elongates, energy density decreases, penetration reduces. However, for reflective metals like aluminum and copper, a slight angle is required. This prevents back reflection into the laser source, which can damage optics and reduce system life. So the rule is simple: vertical for efficiency, slight tilt for safety when needed. 5. Joint design. Joint geometry directly controls weld formation. Laser welding produces a narrow and deep weld, so joint fit-up must be precise. Large gaps are not suitable. Energy cannot bridge wide gaps effectively. Common joints include butt, lap, and T-joints. Each requires different parameter tuning. For thick materials, proper groove design improves penetration. For thin materials, tight contact ensures stability. Poor alignment leads to uneven melting and weak joints. Joint design is not secondary, it is fundamental. 6. Wire feeding speed. In filler wire welding, energy is shared. The laser must melt both base material and wire. If wire speed is too high, energy is consumed by the wire. Base material receives less energy, penetration decreases, bonding weakens. If wire speed is too low, the joint is underfilled. Surface may collapse or lack reinforcement. Wire feeding must synchronize with power and travel speed. Stable feeding leads to stable molten pool behavior. Oscillation. Oscillation introduces controlled movement to the beam. Instead of a straight line, the beam follows a pattern. This redistributes energy. Benefits are clear. It enlarges the weld width, it stabilizes the molten pool, it reduces porosity by improving gas escape, it improves tolerance to joint gaps. 2 parameters matter. Amplitude controls width. Frequency controls how fast the beam moves. Too large amplitude reduces penetration. Too high frequency reduces effective heating. Correct settings improve consistency and reduce defects. 8. Shielding gas. Shielding gas isolates the molten pool from air. Without protection, oxygen and nitrogen react with molten metal. This creates oxidation, pores, and brittle structures. Argon is stable and widely used. Helium provides deeper penetration but costs more. Gas flow must be controlled. Too little flow gives poor protection. Too much flow disturbs the molten pool. Delivery method also matters. Coaxial flow gives uniform coverage. Side flow is simpler, but less consistent. Stable gas protection ensures clean and strong welds. 9. Other critical factors. Surface condition comes first. Oil, rust, and contamination reduce laser absorption. They introduce gas into the molten pool. This creates porosity and cracks. Cleaning before welding is mandatory. Preparation is next. Laser welding has fast heating and cooling. Impurities do not have time to escape. Defects are easily trapped. Positioning and clamping are also critical. The laser spot is small. Deviation leads to missed joints or uneven welds. High precision alignment is required for stable results. Closing. These 9 factors work together. Power, speed, focus, angle, joint design, wire feeding, oscillation, shielding gas, and preparation. If one is wrong, the weld quality drops. If all are controlled, the process becomes stable and repeatable. This is how you move from trial and error to controlled production. Thanks for watching. Subscribe for more practical laser welding training. See you in the next video.